It is now 8:03. So we are going to go ahead and get started here and let people trickle in if they're running a little bit behind. Okay, so thank you everyone for joining us today. We really appreciate you taking the time. We know that everyone's in different time zones and sometimes that can be challenging, getting up extra early or staying up extra late just to join us, and we can't tell you how much we appreciate that. I hope that you were all able to join us on our previous MBBR webinar, in which we discussed kind of the basics of MBBR and what SSI has to offer. Today, we're really going to be diving into design considerations and some case studies. Let's see. So inside the presentation today, we will be reviewing basic MBBR design. This is going to be a domestic design, pretty simplistic compared to how complicated and complex you can get with MBBR. We're going to review the biofilm carrier selections, different impacts on the design of the MBBR system. Then we're going to dive into industrial considerations. So after learning about domestic, we're going to learn about how the design process would change when you're looking at different industries. And then we're going to dive into two different case studies, one on a textile and one on a dairy. And this is our SSI Process Team. I am Kelsey Bennett, a process engineer. Later on, Jason Bowman, our process manager, will be taking over to review the industrial considerations and the case studies. And Bob Fredenberg is our director. He's on the call here today too. I would just like to remind everyone that you do have the ability to go into the chat room to ask questions at any time. Our team is here. They will be fielding questions. If there is a question that requires somewhat of a more complex answer, we will wait until the end of the presentation. We'll have a Q&A. So you can ask questions in the chat room, or you can ask questions in what's called the Q&A, which you'll see on your screen. Those questions will be saved there till the end, and either Jason or myself will go into an answer of that for you. Hopefully we'll be able to get all questions answered today. However, we do understand that we are just kind of breezing through the basics of MBBR design today, and there's so many different caveats and so many different situations. So depending on the amount of questions we have and the level of detail we're asked to go into, we may need to do a third MBBR webinar to do an even deeper dive into some of your questions. But for the sake of time, because we don't want to keep you here longer than an hour, we are going to get started. So MBBR 101, as you have learned just throughout the industry and perhaps on our previous webinar, MBBR varies because opposed to being a suspended phase biological system, it is actually attached. So the biology is attached to engineered biofilm carriers, and that's where we're going to get our biological treatment. There are many different configurations. There are many different configurations that MBBR can be placed in depending on the treatment requirements. Here are a few here. Today, we are just going to be focusing on the removal of BOD-COD. We're going to be focusing on a one-stage MBBR followed by clarification. We are also, in the beginning of this presentation, going to be focusing on only domestic water. I know that that might be a little frustrating, but we have to start off with the basics in order to move into the more complex systems of the industrial waters. So just my page turner isn't working here. Let's see. Oh, so here you go. Here's a reminder how the biology is attached to an engineered biofilm carrier. This is the MBBR system. So a little MBBR history. The father of MBBR is Professor Alvard Odegaard. He invented the MBBR in Norway in the late 1980s. There have been successfully running MBBRs for over 30 years. And historically, when you look at the first 2 decades or so of MBBRs, they were designed with coarse bubble aeration due to maintenance issues with accessing the aeration grids. And if you go back to the 80s and 90s, fine bubble aeration was not where it is today. Historically, we also saw more conservative hydraulic retention times, meaning slightly bigger tanks, and we were using simple low surface area biofilm carriers. Although Professor Odegaard has done the most research into MBBR than anyone else, there's also many independent studies and ongoing research from Odegaard and others that have created a lot of innovation in MBBR, especially in the last decade. There have been studies on the structure and development of the biofilm and the metabolic functions, so we understand the capabilities and limitations of this system much better. Another example, there's actually been ongoing research the last 5 years where we are mapping the DNA of the attached biology versus the suspended phase biology, so we can see the differences in what we're able to grow and therefore what different treatment we're able to achieve. Well, there's been a lot of exploration into EPS, which is the protective layer around the biology, and also simultaneous treatment with biological layering. So there's been a great article released recently about simultaneous nitrification and denitrification within the different layers of biofilm on a biofilm carrier. There's also been a lot of advancements in fine bubble technology. We have PTFE now, we have more durable diffusers, so maintenance issues aren't an issue like they were in the past. We're able to optimize mixing patterns and efficiency and even maintenance. There's also been advancements in media development. As you may have seen, there is a wide variety of biofilm carriers on the market today, anywhere from the original K1 all the way to a chip or foam style media. However, I do want to note that not all innovation has been good. One example of innovation, quote unquote, innovation for MBBR we have seen in last years is using cut golf balls and Gatorade caps as the biofilm carriers. And as you can imagine, that did not turn out too well. Those MBBR systems did not function properly, and that can give a bad reputation to MBBR, which is unfortunate because MBBRs provide so many benefits and capabilities, and we want everyone to be able to take advantage of those. Oh, sorry, here's just a little clip of media throughout a tank with a fine bevel diffuser. So before we dive into designing an MBBR system, we need to define what a healthy MBBR system is so we know what we're striving to design. So first and foremost, we want to have a healthy biofilm thickness. Now, a healthy biofilm thickness does not mean the most biofilm thickness. The uniform, the typical optimal diffusion layer of biofilm is about 200 microns. So if we were to increase the biofilm to, sometimes we see up to 1 micron, you're really not achieving as much treatment. You don't have as healthy as a system. So what we want to see is something like here on the left, where you have biofilm attached to the carrier, but you have a great open area that allows water to go through the carrier. So you have diffusion with the aerated system, and you're able to achieve optimal treatment with all of your biology. You also need to have uniform distribution throughout the tank. As you can see here in this image, there are biofilm carriers floating all around the tank. They're not just floating at the top, they're not just sinking to the bottom, there's uniform distribution. The reason why that is so important is because if you do not have uniform distribution of your biology, your water can short circuit, it can go around the biology, and you're not going to receive treatment. So optimal biofilm layer and optimal distribution throughout the tank, that's what we're going to strive for right now as we go through our design. So how do we design an MBBR system? First and foremost, the first step that I think a lot of people tend to pass over is defining the problem or project. And unfortunately, I am going to pass over a little quickly today, but I want to emphasize how important it is to understand the specific water chemistry for the project you are looking at. Every single project is going to be different, and it's going to require a different approach to the design. It's really important not just to understand how much BOD you have, but to understand the plant holistically. What treatment do you have upstream, downstream? Understand the water chemistry holistically. Do you have enough alkalinity? Do you have pH imbalances? Is there any toxicity in the system? We'll dive into all of those a bit more in a second. But we also want to check to make sure that the project you are looking at is a good fit for a biological system. This doesn't happen very commonly, but sometimes we do get clients who may come to us and say, hey, I have a system at this flow rate, and here's the COD and here's the BOD, and we don't know anything else about it. Not all COD is created equal, and we saw a very high COD to BOD ratio, which caused us to ask more questions, and we found out that this is coming from a glass facility. Well, the COD that's coming from a glass facility is likely not going to be biodegradable, and you're going to need to use more physical treatment than biological treatment. So it's really important to understand that as well. So after you've defined the problem, the next step is to find the volume of media needed. This directly correlates to how much treatment you can achieve, how much biology you can grow within the system. It's going to be based off of your treatment requirement. And then after we know how much media we need, we're going to design the reactor configuration. The aeration system and the media retention screens are also very important to ensure that you're designing a reactor that has proper hydraulic flow through it and kinetics so that you have that uniform distribution. So step one in designing an MBBR system is to figure out how much media you need. Now, theoretically, there are two main equations that can allow you to figure out how much media you need. This is going to be based off of the surface area loading rate, the protected surface area of the media, and the daily load of your constituent. So like I said, we're just going to be talking about BOD domestic systems right now. So when we talk about daily load and loading rate, we're talking about BOD. So how much BOD is coming into your MBBR on a daily basis, and how much protected surface area you have of the media. However, there's a few things I want to emphasize here. First, we want to make sure that the daily load is the daily load into the MBBR, not the daily load coming into the plant, because pre-treatment is definitely going to impact how much you have coming into the MBBR. Second, which we'll go into more, is that instead of using protective surface area, what we really should be using is effective surface area. Like I said, there's been a lot of innovation in MBBR research the past few years, and we understand that protected surface area does not directly correlate to the area that is available for biology to grow on. And thirdly, I want to talk about the loading rate. You'll see a lot of studies online when you do your research. You'll see a lot of equations using SALR, your surface area loading rate. However, when we're really designing our plants and we're trying to figure out how much media we need, we want to be using the surface area reduction rate. This is how much reduction you can achieve in your MBBR system. So we're going to dive into all three of these different variables in a little bit deeper here. So what is your surface area loading rate? So surface area loading rate is a measurement of the daily load, your daily BOD load, across the total protected surface area of your media. Okay, really what it's meant to be is it's meant to be a measurement of how much load can my system handle. Okay, so instead of thinking of it as, oh, I can just pick a surface area loading rate and therefore that will tell me how much media I need. Instead, it should be looking at your system, looking at it holistically, and figuring out how much can my system actually handle. So unfortunately, there's no cut, dry answer to what your loading rate is going to be. It's actually an empirically derived variable that has been researched over the last 30 years, and we're still continuing research on. The factors that impact the loading rate that your system can handle include media geometry, biofilm thickness, predation in your system, the diffusion through the media, any biodegradability of your constituents, toxicity that may be present, alkalinity or pH imbalances in your system, suspended solids, fats, oils, and greases that could be in your water, and primarily temperature. Because your loading rate is basically saying, how much treatment can I achieve? And that's really dependent on your biology, right? And so the kinetics and the metabolism of your biology is going to be significantly impacted by temperature. So does your loading rate actually indicate treatment? I've kind of touched on this a little bit. To capture the treatment efficiency, we want to use the surface area reduction rate. This surface area reduction rate directly correlates to your surface area loading rate. So typically for a domestic wastewater system that has no toxicity issues, has no pH or alkalinity imbalances, has relatively low suspended solids and fog, you may see a treatment efficiency of about 90%. Therefore, your reduction rate, the amount of treatment you're able to achieve, is going to be about 90% of your loading rate, okay? So one thing to note here is that if you overload your system, if you have too much BOD per amount of biofilm carriers that you have, your efficiency, your treatment efficiency is going to drop. Your biology is not going to be able to treat as well if the load is too high. So once our loading rate starts to exceed about 20 grams of BOD per square meter of surface area of your biofilm carriers, efficiency is going to start to drop to 70 or 80%. So it's a fine balance of figuring out what your system can handle in terms of the loading rate and what it's actually going to be able to achieve with the reduction rate. I also want to point out here that when we are looking at an MBBR system and how much treatment it can achieve, we're really looking at the soluble fraction of BOD. It's very important to understand not just how much BOD you have in your system, but what is the fraction of insoluble to soluble. If your BOD is in particulate form, it's better to separate that out via a primary clarifier or maybe even secondary clarifier tertiary treatment, because it's not going to be broken down in the biological system as easily as soluble BOD. Particulate BOD is going to take a longer time to assimilate and therefore a longer time to break down. So this is just a little blurb about how when we're actually designing the system, we want to use the reduction rate in our equation, but first we need to determine our loading rate. And the reason why I'm focusing so much on loading rate is because when you do your research online, when you look at technical articles, when you look at research studies, you're primarily going to be seeing things measured as loading rate. So how can we estimate a loading rate for our system? Like I said, it's empirically derived. There's so many variables that impact it. So as engineers, when we're looking at a new system, how can we estimate what loading rate our system can handle? And like I said, there's no universal equation for loading rate, but the variable that impacts it the most is temperature. So typically you're going to see logarithmic correlations between your loading rate and your temperature. And remember, temperature directly impacts the kinetics of your system, right? So as temperature increases, you're going to have higher metabolisms for your biology. You're going to have higher reaction kinetics. So you're going to be able to achieve more treatment. As your temperature decreases, those kinetics slow down, the metabolism slows down, you're not going to be able to achieve as much treatment. So your loading rate is going to decrease as well. You can see here some examples of SALR curves versus temperature. There's 3 different curves here just to show you that one curve can vary depending on the industry or depending on the type of media. There's not one curve that fits all. So one analogy that I really love that I heard recently was that if you find a study online, let's say that gives you an equation for SALR compared to temperature, extrapolating that equation for maybe the study was based off of a K1 media, extrapolating that from a K1 media to then determine what you can treat with a high surface area media, that's like extrapolating the miles per gallon for a Honda Fit to an old Jeep, right? Just like I couldn't say, hey, I can get 50 miles to the gallon in my Honda Fit, therefore in your old Jeep, you should be able to get 50 miles to the gallon. It doesn't work that way, right? They're completely different vehicles. And similarly, with biofilm carriers, I can't look at a study that tells me how much treatment I can get with 1 cubic meter of media and extrapolate that to the same amount of treatment with 1 cubic meter of media of a high surface area. So the bottom line I want you to take home here is to pay very careful attention to the studies and equations that you find. Make sure to note which type of media and which type of wastewater they are based off of. Now, we understand that not everyone can do pilot studies on their systems, right? Ideally, we would always like to do a pilot study on whatever water we're going to treat to be able to determine our loading rate, but we can't, right? So we have to look at these studies, we have to look at these different equations, but we need to understand how those differ from our in particular system that we're about to design, okay? So selecting the right media, let's say that you found a study, you found an equation for surface area loading rate that has a wastewater very, very similar to the one you are going to be designing for. That's wonderful, right? But what if you want to use a different media than what the study is using, right? How will your loading rate differ from one media to the other? And the bottom line here is that actually what studies show is that medias with higher surface area actually result in lower loading rates. So if you know what the loading rate is for a K1 media, but then you want to move to a chip media that has a very high surface area, you're going to have a significantly lower loading rate, okay? And again, this is all because of what we need to achieve with a healthy system, right? We talked about this a little bit before, that if your pores are too small, you may have very high surface area, but the biofilm can't actually grow within those pores. You can't actually get diffusion through those pores. And so that's why as you go to higher surface area, you get smaller pores, you actually get less diffusion and therefore less treatment. So studies, what we have found, and these are also from third-party studies as well, is that the optimal range for your protected or effective surface area is actually between about 500 and 800. And when we're talking about domestic wastewater, which is what this is for here, you can expect to see about 12 to 15 grams per square meter loading rate for a domestic system if you are using a media that is between 5 and 800 square meters per cubic meter. Once you start to move to a very high surface area media, you start to go over 1,000 and even up, your surface area loading rate is going to significantly drop off. So the main thing that I want to emphasize here at the top is that media it's not just a piece of plastic, it's engineered, and the geometries are designed specifically so that we can have that optimal diffusion area, we can have that optimal surface area loading rate. But there's other factors in choosing a media. It's not just about geometry, it's also about material properties. And every media is going to be different. So when we're talking about achieving optimal treatment, we also need to make sure we have a media with the proper properties. Surface area is not the most important. And what we see here is we see a little, a kind of cyclical system where we do emphasize surface area so much in our industry because modeling only accounts for surface area. If you were to go into BioWin or Sumo or any of these types of wastewater models, typically the only characteristic they're looking for when talking about biofilm carriers is what the surface area is. And what that has led to is kind of this space race for a high surface area media, right? Because if you have an engineer who's looking at a modeling system, they say, oh, well, if we have more surface area, we're going to have more treatment. But as we know, that's not the case, right? Because more surface area, like I showed on the last slide, does not correlate to more treatment. In fact, higher surface area means a lower loading rate. So we have this space race for high surface area. We have very high surface area medias. Then we design a system that doesn't have enough media. We don't have enough biological growth. And then we have a failed MBBR system. And we really don't want that to happen. So we need to pay careful attention to not just the surface area, but also to the other properties of our biofilm carriers. What are the hydrodynamics? What can I load into it? What's the mixing energy? And what's the strength and longevity? And so when we're talking about biofilm carriers, we really want to focus on high quality version HDPE, okay? There's some medias out there that might use other, PE or PP. They're not going to have the right density to move throughout the water. So we need to make sure to have uniform distribution, that we have the right buoyancy of media, right? We want to have a media that has a specific gravity of 0.95 to 0.97. Anything lower than that is going to mean that our media is going to float. It's not going to be uniformly distributed throughout the tank. It's also very important that we have proper strength. This is not just about wall thickness. Wall thickness does provide strength, but strength also comes from the property of the HDPE material. So HDPE can vary. High quality version HDPE is going to give you the best strength. That's going to give you the best longevity and strength over time. When you're designing your MBBR system, you want to design it so it's going to last 20 years, okay? So let's say we have selected our MBBR biofilm carrier, now that we've talked about how to select those, right? How can we estimate our surface area loading rate for waters other than domestic? Let's say I found a study and an equation that fits my biofilm carrier, but doesn't fit the water I'm looking at, okay? We're gonna dive into this a bit more in a minute, but I just wanna emphasize here that there's no plug and play equation to estimate the impacts on surface area loading rate, okay? It takes research, it takes experience, and it takes a holistic understanding of the wastewater system at hand to be able to identify and estimate the potential impacts, okay? This could be the type of wastewater, the biodegradability, the type of COD, toxicity that's present. All of these are going to impact your surface area loading rate. Some negative impacts here. There are many different factors that can impact your SALR, but I just put a few here. High COD to BOD, if you see a ratio that's greater than 2 to 1, that can start to indicate low biodegradability. High TSS to BOD ratio, anything greater than 1.5, that can start to indicate that the amount of suspended solids you have in your system, those could start to interfere with the ability for your biology to grow, right? If you have solids that are kind of floating throughout the system, that can impact your growth on your biofilm carriers. High fats, oils, and greases. We say 20 milligrams per liter is about the highest point. That's about on average. We can peak up to 30 milligrams per liter and still be okay. But once you get a lot of fats, oils, and greases in any biological system, you're going to start hindering the kinetics. You're going to start hindering the treatment. So you're going to have a lower loading rate. Any toxicity, low alkalinity, or pH imbalances are also going to lower the loading rate that your system is able to handle. So, but I just want to touch here though, that we've talked about water chemistry, we've talked about loading rate, we've talked about biofilm carrier selection, but in reality, when we're designing an MBBR system, when we're trying to figure out what our MBBR system can handle, what it can treat, it's much more holistic. We also need to understand what's going on upstream and what's going on downstream. So upstream, you might have screening and grit removal, boil water separation, or primary clarifier. Primary, it's kind of a cyclical thing, right? So we need to make sure we have enough primary treatment to be able to have healthy biological treatment. But at the same time, we can also change our biological treatment design by changing our primary treatment. So for example, if we invest in advanced screening, we could potentially reduce our MBBR size by up to 30%. Of course, this is very dependent on the soluble and insoluble fraction of BOD. If we have a high particulate fraction of BOD, we're going to be able to achieve a lot of removal with perhaps screening or a primary clarifier, and therefore we don't need to have as much treatment in the actual MBBR. So our MBBR can be smaller. So all of these impact the design of the MBBR and the clarifier. But then also we have tertiary treatment downstream, and this is going to impact what we need to achieve in our MBBR system. So all of these together need to be looked at holistically. They all impact each other. It's very difficult for us to design an MBBR system independent of understanding the entire treatment process. So just a quick review on what we have covered so far. We know that we can find the amount of media that we need, the amount of media that's required for the treatment we are trying to achieve by understanding what our daily load is. That's going to be the BOD reduced in the MBBR system. By understanding what our effective surface area is from our media selection. And that's going to be kind of the culmination of what the protected surface area is and the pore size, right? Making sure we have proper diffusion. And understanding what our reduction rate is, which means we have to understand our loading rate, we have to understand our efficiency, and these are going to be very project specific. Once we understand these three variables, then we can find the total volume of the media that we need. Next, I'll dive into a little bit about how to design the actual reactor. But first, I want to real quick just talk about why we can't use the equivalency method to design MBBRs, okay? So historically, most of our systems, especially here in the US, are conventional activated sludge systems. These rely on suspended phase biology, MLSS, within the system, right? When we're designing a conventional activated sludge system, what we see is that there's a direct correlation between the amount of biology and the amount of treatment, okay? So increasing your MLSS may be able to increase the amount of treatment you have because you have more biology in your system. That's not the case for MBBR systems. If you recall, the optimal diffusion is only 200 microns on a biofilm carrier. So if we increase our biology to 1 micron on that biofilm carrier, we're not going to achieve any more treatment. This tends to be an issue, like I said, with models that assume that more biomass means more treatment, which is not the case in an MBBR system. Furthermore, it's actually very difficult to accurately predict the thickness of the biofilm that is going to grow on the biofilm carriers. And we don't spend too much time trying to predict that because we know that if we design our system properly, if we take into consideration all the different variables, if we select the right amount of media, that we're going to grow healthy biofilm independent of how thick it's going to be on the media. And we're going to be able to achieve proper treatment. So now let's dive into a little bit, we know how many biofilm carriers we need. So designing the tank, we're going to set a volume so that our biofilm carriers are going to fill the tank between 30 and 65% to make sure there's uniform distribution throughout the tank. If we go less than 30%, there won't be enough uniform distribution. You're not going to achieve treatment. You're going to achieve short circuiting. But once we know that we have proper uniform distribution, how do we design the aeration system? Well, two things are important when considering an aeration system. One is to make sure that you have the proper mixing patterns. So we use full floor coverage, which means a minimum density of about 7 to 8% of diffusers on the floor. This ensures that you don't get any roll patterns within your tank so that you're actually mixing your media properly and there's uniform distribution. We also use 2mm PTFE discs because these have greater resistance to foul and creep. Like I said, one of the downsides to fine bubble aeration in an MBBR system in the past has been the operators not wanting to drain their tanks to clean the fine bubble membranes once or twice a year. When you drain a tank, obviously the media is going to be at the bottom of the tank. It's going to make it more difficult to access the grids. That's why people like to use coarse bubble in the past. Now that we have PTFE, we have this greater resistance to foul, we have greater resistance to creep. We have many instances, we can talk about it more in our SSI aeration webinars, where operators are able to go 5+ years without having to drain the tanks to do any maintenance on those membranes. We like to use 2 millimeter because they have greater resistance to foul and creep, but also because they're more of a medium bubble, which is better for mixing energy with the MBBR biofilm carriers. They also have really great turn up and turn down flexibility. And with these systems, we see about 30% energy savings compared to using coarse bubble with an MBBR system. So that's why it's really important. Once you switch to fine bubble aeration, you're going to be able to achieve a more efficient system. This is a great benefit to you, to your client, and it has a better, more robust and efficient system over the long term. We do not like to use tubes in MBBR systems. They simply create different patterns and the media interacts with them a little differently. It's not that they're bad to use in MBBR systems, but we simply prefer to use discs. One other thing to note when you're designing the aeration system is the mixing energy required for your system. So there's the airflow needed to achieve your 3 milligrams per liter of dissolved oxygen, but there's also airflow needed to achieve proper mixing throughout the system. Typically, we see that the airflow requirement for dissolved oxygen is higher than the airflow requirement for mixing energy. But there are some situations, especially in retrofits, when the tank is larger than what it could be, where mixing energy is actually the driving factor in the aeration design. So this can be very important when looking at which biofilm carrier you're going to select. Not all biofilm carriers have the same mixing requirements. It's due to the geometry, due to the material properties. And what we find is that, here's a study actually that was done. The kind of chip and foam medias require a lot more mixing energy, sometimes 5 times more than a media such as the SSI media. I also just want to point out here that this has been verified by third parties recently. There was a pilot study done comparing different types of media, different types of HDPE materials, and the SSI media actually had the lowest mixing energy. And that was because we specifically designed our media to have low mixing energy, to have the best buoyancy, to have a good geometry, and we used that high quality virgin HDPE material that gives us the properties we need for that. So just keep that in mind when designing your MBBR systems, that every biofilm carrier is going to have a different mixing energy. Media retention screen design. So once you have your tank figured out, you have your aeration system figured out, now we need to have media retention screens. This is so that our media doesn't flow through the MBBR and into our clarifier. We here at SSI, we use wedge wire retention screens. You can use perforated plate. However, wedge wire is preferred because there's a larger percent open area. Typically with perforated plate, we may only have 35 or 45% open area, whereas with a wedge wire screen, we'll be seeing 65 to 75% open area. What that open area allows us to do is reduce the head loss in the system and reduce the slot velocity, which is the velocity of the water moving through the open area of the screen. Now, this is important for MBBR design because we want to make sure we have a low slot velocity so that we don't have the media kind of migrating towards the screen due to the velocity of the water, right? We want to make sure that we're keeping the proper hydraulics within the tank. We want to place those media retention screens over the aeration grids to keep the energy from the aeration high around the retention screens to prevent any type of buildup, not just from MBBR media, but also of solids, which brings me to my next point, which is that whenever you are designing an MBBR system, your primary screening upstream of the MBBR system should always be smaller. The slot size should always be smaller than the slot size of your retention screens. And the reason for that is because we want to sift out the particles in the primary screening that could potentially get clogged in our media retention screens, right? If we do this, if we do these steps here, typically we're able to provide a system that has retention screens that don't need any kind of scour or backwash or anything like that. They're able to just be self-sufficient and run without any type of buildup. One other thing I want to mention is that slot size should not be more than 70% at the smallest dimension of the biofilm carrier. If you have a biofilm carrier that's 12 millimeters wide and you have a slot size that's 11 millimeters wide, yes, the biofilm carrier is not going to move through there, but it can still get lodged into that opening. So we use 70% there. And then post MBBR clarifier design, we use rapid clarification. I've mentioned this before in a previous webinar. With an MBBR system, we're not relying on suspended phase biology. So our suspended particles are actually smaller, which means that they have different settling characteristics. They take a longer time to settle. So we use rapid clarification to reduce the settling distance. And because they're smaller particles, we don't see fouling of the rapid clarification. It's a very good fit with them, and you're able to have a smaller clarifier. If you use coarse bubble, however, you are going to have more turbulence in your MBBR system. It's going to be breaking up more of those particles, more of the biology, and so you will have even smaller particles, which is harder to settle in your clarifier. So that's another reason to move to fine bubble aeration, is to increase the efficiency of your clarifier. Just keep in mind here that we typically design our clarifiers for a surface overflow rate between 1 and 2.5. If you have too much hydraulic retention time in your clarifier, we have clients sometimes ask us for like 8 hours of retention time. There's many studies that show once you start to exceed about 4 hours of retention time, you can start to see nitrification in your system, which can cause, denitrification, which can cause gas bubbles and issues with the settling. So now we have gone through all of our design considerations for a domestic system, all the way from how we decide how much media we need, all the way to the reactor design, the retention screen, the aeration, and the clarifier. Now I'm going to turn it over to Jason Bowman, who's going to start to talk about how this design process is going to differ when we're looking at specific industries.
Great, thanks, Kelsey. That was a good introduction. I see a lot of familiar names in the chat group and the text and whatnot. That's good to see. I appreciate you guys joining. Kelsey went over a lot of detail with the MBBR design. What I'm going to try to do is look at some real world cases. I see a lot of you asking very similar questions. How do I design for X facility? How do I design for X flow rate? How do I design for a dairy, etc.? So hopefully we can shed some light on that by showing some specific cases. One thing I want to kind of circle back to is what Kelsey said very early on in the presentation, and that is a lot of people ask, what % fill do I need for my application? And I just want to reiterate that once we have a problem definition and an understanding of the problem objective, the first step for us is going to be to determine the media volume. So generally, we design the reactor around the media volume. That's kind of how we approach greenfield designs. It's also how we approach existing systems and retrofits. In a pure MBBR process, what we look at with everything that Kelsey touched on today, what we try to do is find that media volume first, and then we work around that. Obviously with a holistic understanding, understanding the rest of the plant, the primary systems, secondary and tertiary systems. So I'm going to take a quick break and just check the question and answers to see if there's anything in here that that I will address, or if there's anything that is kind of left over from Kelsey's presentation. I see Dirk here asks, what is a typical TSS value of the effluent after MBBR and after clarifier? Very good question. It will depend on the type of wastewater, and it will depend on the mixing energy in the system, what type of aeration is used. So if we were to look at a typical domestic application, in general, I would say with reasonable certainty, we're going to always be below 400 parts per million TSS directly out of an MBBR. In some cases where we have more advanced primary screening or perhaps a primary clarifier, the solids discharged directly from an MBBR may be as low as 200 in some cases. And then from the clarifier system, we have systems lamella systems operating without chemical addition that can achieve below 20 parts per million of TSS. To get much lower than that, then typically you're going to have some type of coagulation or some type of filtration. So with that said, let's jump into the industrial considerations. Kelsey, if you want to jump to the next slide for me. Oh, Kelsey, are you there? Oh, there you go. Thank you. So focusing on some real world applications. So over the past few years, we've seen an increase in slaughterhouse design, slaughterhouse inquiries. As the population increases, so does, the human need to consume meat. So there are different types of slaughterhouse processes. I think we're all aware. Obviously, different types of animals and different types of processing even. In some cases, we're looking at slaughterhouses that have the entire process from, the butchering process through the meat preparation and packaging process. So each one kind of carries a different design perspective. Some of the most common things we see with slaughterhouses are going to be high levels of COD, BOD. There's also a lot of proteins in the wastewater, amino acids that typically comes from like the butchering process. In some places where blood is introduced into the system, we'll see high levels of iron. So when we approach slaughterhouses, we generally look at it as a holistic approach. It's difficult to design just the MBBR process without knowing what's upstream. If there's any primary treatment in place, just giving a BOD value or a COD value in a slaughterhouse application can be very, I'd say, risky for biological system design and MBBR system design, just because we have kind of a complicated wastewater coming in. The first thing we typically look at is the primary treatment. And in most cases, we're going to consider some form of advanced screening or dissolved air flotation. I would say, based on my personal experience, dissolved air flotation is used in most slaughterhouse applications that I have been involved with. They tend to be very compact, very high rate. They do an excellent job of separating oils and greases and solids. So you will find in a lot of cases that DAF and MBBR fit very well together for that reason. Both the DAF and the MBBR system are probably one of the more compact biological and solid separation systems that you can find in wastewater treatment. So in a lot of cases in industry where footprint and real estate is comes at a high cost, DAF systems and MBBR systems take up very little space. So they're a lot of times they're preferred in these cases. So earlier in the presentation, someone had a question about aeration design for MBBR's industrial treatment, domestic treatment. You'll notice in the next few slides that I mentioned aeration design as it pertains to the specific wastewater chemistry and the specific process water. So using slaughterhouse as an example, often what you find is due to the high levels of COD and BOD, you need elevated volumes of media because we're typically using a more conservative surface area loading rate for the media, just so we don't, just so we can minimize the amount of inorganics that go to the biological process. But further to that, with such a high COD, a high BOD, and maybe extended hydraulic retention times, we typically need to upsize the aeration system, specifically the amount of kilograms or mass of oxygen per mass of BOD removed. In general, with aeration design, the longer retention time you have, longer solid retention, longer hydraulic retention time, the need to have a higher mass of oxygen to BOD is required. So focusing back on the MBBR system, When we look at the surface area loading rate, I mentioned it's a little more conservative. Most of what I mentioned in my slides and moving forward is going to be based on what we consider a 90% removal efficiency. So all of these surface area loading rates should correlate to a 90% removal efficiency. So with everything considered in the plant, primary systems are in place, primary systems are a check. We would generally look at using somewhere between 7 and 10 grams per square meter as a surface area loading rate for a slaughterhouse application. Then we have to focus on the amount of biological solids that come out of the system. So then we have to look at the secondary treatment as well. Lamellas are typically a good fit. Depends on the space requirements, depends on the TSS requirements. In a lot of cases, a secondary dissolved air flotation system is also used. Historically, MBBRs that used coarse bubble aeration generated a lot of pin flock. So that's why in a lot of cases you find MBBR and DAF systems work very well together. Based on our experience, when we combine MBBR with fine bubble operation, we see less pin flock formation and much better settleability and clarifiers. So in most cases, we're going to design using a lamella system. Kelsey, next slide. All right. Fisheries, both the processing and farming aspect is a growing business, particularly in overseas, like in our Asia countries. We see a lot of inquiries for fisheries. Fisheries carry a very unique design perspective, because in most cases it's not a pre-treatment system or not a surface water discharge system. You're actually talking about sustaining life, being able to sustain a population of fish. So treatment is extremely critical in most of the farming applications. So depending on the raw water source and what type of farming or what type of fish or what type of processing, there could be a significant amount of nitrates, proteins, amines. Alkalinity control is critical in most of these cases. On the processing side, alkalinity is critical because of the pH issues. With processing with fish, a lot of times what you find is a high degree of ammonia or ammonium. So being able to fully or completely nitrify obviously consumes alkalinity. So we always make sure that we have some type of alkalinity control system in place and that we understand exactly what our alkalinity is. In a lot of cases, these fish processing facilities or fish farming facilities are based on lagoon or pond treatment. And water temperature can be an issue due to fluctuations. In a lot of cases, people are trying to control the temperature depending on the specific type of fish. So we need to make sure that those systems are in place and that we understand, the temperature fluctuations and how temperatures are going to impact, this particular application. In the farming industry, the threshold for toxicity is very critical, because any free ammonia in the system can be potentially fatal to a fish population. And this kind of goes back to the alkalinity control. If pH gets too high, what happens is the form of ammonia shifts from ammonium to free ammonia, which is the more toxic form. And it doesn't take much, very few parts per million of free ammonia to really have a detrimental impact to fish population. So when we approach these designs, we typically are more on the conservative side just for that reason. We want to make sure that we can absolutely achieve the effluent criteria, the effluent goals, and that we're sustaining, the fish population, making sure that everything stays healthy and stays alive. Kelsey, next slide, please. All right, food and beverage is perhaps one of the most, probably the highest volume of inquiries that we see for industry globally falls in the food and beverage category. And I don't think that's going to change. as the population increases, the demand for, quick delivery, and, accessible, accessible food and beverages is only going to increase. So you see a lot of small facilities popping up every year. So this tends to be one of the most design projects that I think here at SSI that we work with. So food and beverage it really has a wide range. You think about soft drink production or refreshment production, confectionaries, bakeries, it's really all over the map. But one of the commonalities between most food and beverage applications is high BOD, high COD. A lot of organics go in the system, a lot of sugars. Most sites are biodegradable or highly biodegradable. Obviously, you're not going to manufacture food that you can't digest, or at least you're not supposed to. So most of what we run into is usually highly biodegradable. Each site presents its different challenges. The more sugars and the more salts that go into the process can create challenges with TDS, high color, high dissolved substances, high dissolved sugars, dissolved salts, things like that. So when you start talking about high TDS, depending on the discharge requirements, sometimes some form of tertiary treatment may be required. In some cases where you're going to surface water discharge or ocean discharge or something like that, it may not be a huge issue. But one thing I want to point out is that TDS can actually impact the biological design. I think a lot of people really underestimate how dissolved sugars and salts may impact the oxygen saturation in a system. If you think about the ocean, for example, with high salinity, high TDS, the ocean actually has a lower saturation point than clean water. So it's very similar to what we would find in food and beverage and sometimes in textiles even, that the saturation point is actually quite a bit lower than people expect. It does also have an impact on the oxygen transfer. So the reason why I bring all this up is in a lot of cases, we find that the MBBR aeration system may actually end up driving the reactor design. Let's say we determine the volume of media that's required for this specific application, and then we focus on the aeration portion, how to integrate the aeration into the reactor. In a lot of cases, the maximum diffuser density is what drives the reactor area. For most of our systems, as Kelsey pointed out, our preference is to use disc diffusers, and this is because 100% of the disc area is activated. That is, 100% of the area has oxygen actually flowing out of it. So there's very little risk that the media will impact the top of the diffuser, of a disc diffuser. With tube diffusers, that's not always the case. A lot of people prefer tubes because they have a lot of flexibility, high flow rate. They can get a very high density in the tank. However, with tubes, if they're not designed properly, the membrane of a tube system is not always fully activated. There may be a small portion on the bottom of the diffuser that isn't activated, and over time, it is possible for MBBR media to actually touch that membrane surface. So this is why we typically recommend using a disc diffuser instead. So with disc diffusers, we typically design to a maximum of 25% diffuser density. So when you're talking about high BOD, high COD applications, and if you go back to the previous slide where we talked about slaughterhouses, a lot of times what we find is that we increase the mass or the volume of oxygen per mass of BOD removed. Therefore, we end up with a slightly larger aeration system. So that is going to drive the reactor area in a lot of cases. One of the critical things to watch out for with really any biological system, but more specifically aeration design and MBBR design, is calcium phosphate. For those of you who have worked in dairies or worked in food and beverage, you've probably seen that calcium phosphate can basically stick to just about anything or precipitate. I have seen reactors that have 1 or 2 feet of calcium phosphate precipitated at the bottom of the reactor that have basically covered the aeration system. We always make sure that we understand what chemicals are going into the system. Some soft drinks will add phosphoric acid for taste. Some systems add phosphoric acid for pH control. If there's excessive calcium in the system, which in a lot of times there is, the two can combine under the right conditions and can precipitate out in biological reactors. So very careful consideration. With that said, with the physical MBBR process, the physical design, most applications that we run into, we're looking at a surface area loading rate between 10 and 16 grams of BOD. In most of these cases, there either isn't a stringent nitrogen requirement or there's not enough nitrogen in the system to really consider. In fact, when the COD and BOD is high in a lot of these cases, most of the nitrogen coming into the MBBR system is used as nutrient. So you really find that you're not really nitrifying because there's no ammonia left in the system because most of it has been consumed. Kelsey, next slide, please. Thank you. Pulp and paper is another application that I would say probably once a month we get inquiries for. In most cases, MBBR has been used as pre-treatment for pulp and paper just for the space efficiency. In a lot of these cases, a lot of pulp and paper industries are very old, very outdated. Most pulp and paper plants were created a long time ago, at least in US and Europe. So most of them are established and using older technologies. As the plants grow, so does the consumption, liquid consumption or wastewater consumption. The flow rates tend to increase. BOD or COD may increase. But more recently, what's happened is the regulatory pressures. What you find is a more stringent effluent required. In most cases, most of what I've seen from personal experience is MBBR used as a pre-treatment step, just because a lot of these systems already have, large clarifiers or large activated sludge plants, just because they've been around for a long time. So MBBR is added as a space-efficient way to basically provide a roughing or pre-treatment for BOD and COD. With that said, there are plenty of systems that use MBBR as the actual, main biological treatment component. So I don't want to discourage people from thinking about it that way, but most pulp and paper plants that you see are consuming lots and lots of wastewater. Most of the statistics, I think pulp and paper use more water per kilogram of product produced than any other industry. Maybe with the exception of oil, gas, or tires, for example, they tend to use a lot of water as well. So when used as a pre-treatment step, it's a slightly different design since we're only trying to achieve, let's say a more minimum BOD reduction, say 50% to 70%. The surface area loading rate to the media can be increased. When we use it as the main biological step, however, we use a more conservative design, just because in most pulp and paper plants, there is a lot of calcium in the system. So there can be some inorganic fouling over time that we try to account for. Kelsey kind of touched base on this. Being able to spread not only the organic load across media surface area, but being able to anticipate the spread of inorganic material. If the inorganic material can't be removed in primary treatment systems, then we absolutely have to think about that for the design of MBBR systems. Unfortunately, as Kelsey mentioned, there are a lot of systems in the world that, a lot of MBBR systems in the world that didn't necessarily understand that. And what you find is over 5 to 7 years, the media will foul with inorganic material. when we design MBBR systems, what we're looking for is, the life of the plant, and generally the life of the plant is defined as 15 to 20 years at least. So that's what we aim for. That's what we strive for when we do our designs. So it's just something to, just a consideration to keep in mind. I am going to take a short break and just acknowledge that we have been at it for about an hour. I believe we have about 8 more slides left, and then we can get to question and answers. I see some of the question and answers building up. So at the end, if there's anything more specific or detailed that anyone wants to address, we can certainly do that. So Kelsey, next slide. Thank you. So speaking of real world experience again, the next few slides focus on actual case studies. These are applications that SSI has been involved with over the past few years. So the first slides focus on textile industry. Textile industry is it's an important market. It's growing globally. There are some crazy statistics in Asia where there's something like 5 textile plants incorporated every day in certain parts of Asia. So it's a huge market, a growing market. The demand is massive. Unfortunately with COVID, textile market has been a bit down, but typically these guys, these facilities are 6 months ahead in production. So even though in the Northern Hemisphere, it's summer, they're actually producing for winter right now. So in their minds, they're kind of already ahead of COVID, thinking about the next step. So several years ago, we designed and built an MBBR system for a denim washing facility in Dhaka, Bangladesh. While the flow rate isn't necessarily the highest, textiles have unique challenges in that the COD, BOD varies almost on an hourly basis depending on the production cycle. For those of you who have been involved in textiles, you know that production can change week to week or even day to day sometimes, depending on what orders or what buyers are present. So what we find is huge fluctuation in color, huge fluctuation in TDS, huge fluctuation in COD, BOD. Most of the systems are not readily biodegradable. Most of the systems have a high degree of fiber. Some systems have a high degree of stone, pumice stone used in the washing process. Temperature is also a critical factor in textile treatment. Depending on the collection system, the temperature could be anywhere from 35 Celsius up to 50, 60 degrees Celsius in some cases. When you start getting into like dyeing facilities, print, dye, and finishing facilities typically have pretty high temperatures. So temperature is a main critical consideration in biological treatment design. In most cases, what we're looking for is to try to get the temperature below 37 Celsius for biological treatment. It's not that biological treatment can't work above 37. It's just there is a range between about 37 and 42 degrees Celsius where any biological system is going to have issues because it jumps between, it's basically a boundary between different types of bacteria that can survive. So with systems kind of hovering between that 37 and 42 degree mark, it can create a lot of issues with biological treatment. So if we can keep it above 42 or below 37, we're generally going to be in much better shape. So with this particular facility, it was a holistic approach. We did look at the primary system design. We looked at equalization design. We looked at the biological system and the existing clarifier system. And basically what we came up with was a MBBR process, fairly conservative loading rate. I believe we used 7 grams of BOD for this application to achieve greater than 90% removal. Excellent results over the past 3-4 years. It consistently has BOD levels well below 20. without use of chemical. It has TSS below 20 without use of chemical. Excuse me. So how did we get to that point? Well, part of that was looking at the primary systems. For this particular denim washing facility, we recognized that there's a lot of fiber and stone in the system, so we had to be very careful with the type of primary system that we put in place, as we did not want fibers and stones to make its way to the equalization tank or the biological tank, as that will create issues over time. So Kelsey, if you want to jump ahead to the next slide. So for this particular plant, we only had a 6-hour hydraulic retention time. The system was operated at 33% fill. So for this application, it corresponded to about a 7 gram per square meter loading rate. We used I would say kind of a medium biofilm carrier, having only 650 square meter per cubic meter. The more critical factor that we looked at for this application was the open area, just based on the COD that from the denim washing process and the dyeing process that they had, and based on the fibers in the system, we chose not to use a higher surface area media because we were worried about the inorganic loading over time. So here we are 4 years later, and the system still greater than 90% removal consistently. So I think the design worked out very well in this case. The secondary systems, basically what we used for this application was a PTFE aeration system, disc aeration system. So we used a 12-inch in this case, just for the airflow requirements and the basin geometry. You can see that the drawing, kind of a really bizarre geometry for this facility. Yeah, there you go. Thanks, Kelsey. So one of the things we had to think about was media migration. How do we keep media out of the corners? How do we keep media from moving to one end or the other? So it was a very special aeration design. We had a high diffuser density on this application. We did use a PTFE coating for the aeration systems. Now, we haven't really touched base in this presentation on the use of PTFE, but in 99% of the applications, MBBR applications that we design, we recommend PTFE. PTFE does an excellent job of protecting from biological fouling, from inorganic fouling, and a much better job of controlling back pressure and creep over time. So your standard diffuser uses EPDM rubber membrane. So this is kind of a step above, where we coat that membrane, coat that standard membrane so that it has a protective layer. So for MBBR applications, we use this specifically so that we can reduce the maintenance and reduce the need to get into the reactors with the MBBR media in there. I should state that SSI has PTFE membranes in operation for over 15 years that have actually never been replaced. So when we design our aeration systems, 99% of the time, this is the type of system that we're looking at. One other fact to point out is, in most systems, we prefer to use a 2 millimeter slit for MBBR systems. At low airflow rates, it has similar, if not the same, efficiency as a 1 millimeter device. However, it has a much higher turn-up flexibility. It has a wider range of airflows that it can handle. But it also helps to reduce the pressure in the system a wee bit. And it provides a little more flexibility in fouling over time. A 2 millimeter versus a 1 millimeter is going to have less issues with biological or inorganic fouling over time. So just another consideration that we make with our MBBR systems. So Kelsey, if you want to jump ahead to the next slide. So I mentioned the use of lamella clarifiers. This is a prime example where they had an existing clarifier. Oh, go back one slide, please. Thanks. Where the site had an existing clarifier, and we were trying to get more more flow rate and better effluent solids, better effluent VOD readings. In a lot of MBBR applications, what we see directly from the MBBR discharge is the TSS to BOD ratio, total BOD ratio, is about 1-to-1 in most cases. And if you think about it, it's because most of what comes out of the system is bacteria that leaves the biofilm carrier. So it is a biological solid. It does have BOD, it does have nitrogen, and it does have phosphorus in the biological cell mass. So that's why it registers 1-to-1 TSS to BOD in most applications. So when we need to achieve high levels of BOD reduction, or I should say low levels of effluent BOD, the clarifier design does become very critical to the process. So we want to make sure that we can remove that TSS, that is the biological solids, because it is carrying organics and nutrient. If you can't remove that, then you will continue to have a high BOD or high nitrogen even in the system. So in this particular system, we were kind of limited in space. So the surface overflow rate was quite high, 2.79 meter per hour. We did use a lamella system, 99% tube coverage with a 60-degree incline. By doing this with this particular system, we're consistently under 20 TSS and 20 BOD in the final effluent discharge. So for textile applications, for example, that's typically well below the norms that textiles shoot for. So it was a very good application for us. Okay, Kelsey, next slide, please. Perfect, thanks. So one of the other real-world applications that comes up a lot actually is dairies. And there's a lot of different types of dairies in terms of whether it's milk processing, cheese processing, yogurt or some type of yogurt equivalent processing or manufacturing. So dairies carry their own unique challenges. And I touched base on some of that previously. What I did not point out is that when whey processing is present, whey can contain COD values well in excess of 10,000 ppm COD. So for this particular plant, this client would have fluctuations based on whey in the system on a weekly basis. So it was enough for them to consider treating the whey separately. So in this case, what they did was actually build what they call a calamity tank. So it's a fairly unique process, very sophisticated even. They placed a COD analyzer in the raw influent stream to the wastewater plant. And anytime the COD value registered above, I believe it was 8,000 COD, they would divert the flow to a calamity tank until the COD value decreased. Once that COD value decreased, then the wastewater would proceed to the wastewater treatment plant as normal. In this case, it's kind of a unique setup where MBBR was used as a roughing step prior to a more conventional activated sludge process. And it may be difficult to see in the drawing, but in the dead center of the photo on the top left are two tanks side by side. And these are the MBBR reactors. And then in the bottom right of that same photo is the conventional activated sludge process. And you can see the difference in volume, difference in size. Thanks, Kelsey. You can see the difference in size here. So for this particular plant, we were looking at kind of a peak BOD coming in at about 3,000 BOD, ppm BOD. The effluent goal was to try to reduce below 1,000. I believe the plant consistently achieves about 750 parts per million BOD. So pretty significant level of reduction there as a pre-treatment step before it goes to a larger activated sludge system for polishing. So in this particular case, we see this a lot in industry where clients can't afford to stop the wastewater treatment plant because they can't afford to stop their production process. So I should note in these cases, we either look at a retrievable aeration system or we look at coarse bubble. While our preference is fine bubble, we do recognize that there are many cases where coarse bubble makes more sense just for the client. Even with a fine bubble system in dairy, it will be inevitable that the diffusers will have to be cleaned or have to be replaced. So, and it varies from site to site. So in this case, the client elected to go with a more standard coarse bubble system. So that's what we added to the process, just to minimize maintenance in the long run. So Kelsey, next slide, please. And we touched base on this earlier, but just understanding chemistry in general is kind of, if defining the MBBR media volume is step one, then understanding the chemistry of the system is like step 1 minus 1. So making sure we understand the chemistry of the wastewater and the effluent injectants are absolutely critical. I won't go into too much detail on the specifics of like the dairy wastewater makeup, just because I think we're pressed for time. I do see some attendees falling off, so I apologize. I am long-winded. Kelsey, if you want to jump ahead a few slides to the next, I believe, textile it is. Yeah, I think we can pass this. No, that's it. Okay, good. Okay, well, there you have it. Yeah, I just want to say thanks for everyone for number one, joining, but number two, kind of sticking around. I realize it was a long-winded presentation. If you can't tell, we're very enthusiastic about MBBR design, and we're very proud of our systems. So, if any specific questions, we could spend all day talking about MBBR design. It really is fascinating. It really is unique. Looking forward on a global basis, we're very fortunate that we get to work with each and every one of you across the world. So it's an interesting perspective because we see what's going on and we see the market trends. And right now I can say that in general, MBBR is probably the next replacement for conventional activated sludge. I mean, most systems that we see are moving, most decentralized systems that we see are moving to MBBR design as opposed to conventional activated sludge, just because it's easy to operate, because of the space, simplicity, expandability, all of those factors kind of play into the MBBR, into biological treatment in general. So, we feel like over the next 5 or 10 years, it's going to be a growing market. So we're very excited. I see there are some questions and answers that are still getting.
Yeah, before we dive into the questions and answers real quick, I just want to make one more point here too. I think that we've seen a lot of very specific questions. They've been really wonderful, getting into some more technical detail. I just want to emphasize here that teaching full MBBR design, every single scenario, every single consideration would be an entire class. It would be an entire semester of webinars such as this. This was really meant to be the first basic MBBR design, introducing people who may have never had experience designing in an MBBR before, understanding the different factors that go into it. I understand that there may be a lot of people, a lot of engineers who want to dive deeper, and we would be more than happy to do so. Please reach out to us. We love doing one-on-ones. We find that it's a much easier format to teach and to learn. And so if you and your team want to do a one-on-one with us, please reach out to us. We'd love to do that. We can go through a specific example with you guys. We can go into specific questions that you guys would like to learn about that will help you the most. In the meantime, we also are working on our own internal decision trees and assumptions to we're actually creating an MBBR design software that will be ready by the end of this year. So if you're interested in that as well, please reach out to us and we'll make sure to let you know when that is ready and we can get that up and running for you. And in the meantime, we'll start going through some questions. So Jason, I was thinking maybe I would find some of the questions that I thought were best to bring up right now, and then you could answer them.
Yeah, sounds good. Thanks.
Okay. Jason, bacteria do most of the work. What is the most common problem in an MBBR system, and how do you avoid it?
Very good question. So historically, the biggest issues I have seen are either lack of growth or excessive growth. And it can come down to kind of multiple issues. When you have lack of growth, typically the main factors are inadequate nutrients. So there's not enough nitrogen or not enough phosphorus in the system. On rare occasions, there is too much energy in the tank, and the biology can have a difficulty forming just because the water velocity and the shear velocity is way too high. With a lot of the more like chip or flat type medias, the reason they went to a thinner media was specifically so that they could scour, because what happens is the loading on those type of media can be excessive. So if you reduce the media depth, in essence, you can increase the scour efficiency, but in a lot of cases, it's almost, it can be too much. The other factor for having kind of maybe low growth is just a poor design in terms of surface area loading. There's actually been a lot of studies that suggest, while we talk about surface area loading rate, one would think a lower loading rate would be more conservative. Actually, what happens is if it's too low, you have an issue dispersing the organic loading across the media area. So you don't actually develop a lot of biofilm. And what happens is like higher organisms or higher level organisms will form before the good biofilm does. So the biofilm don't actually really get a chance to stick to the media, so to speak. On the flip side, as you mentioned in your presentation, Kelsey, there is the scenario where your surface area loading is too high, or there's too much organic, or there's too much something else in the system, and that can lead to excessive growth. Maybe not enough scour, not enough aeration can lead to excessive growth. So those are the common issues. And again, I could talk about this all day, but for
yeah. Let's try to get to 2 or 3 more questions, Jason, real quick. We're getting to an hour and a half here. So I picked out 3 more questions here. One is, we mentioned that carbonic acid can lead to filamentous growth in the clarifier. How does that happen?
Yeah, so this is more specific to pulp and paper, I would say. What happens is the CO2 from the process and alkalinity in the process basically combine into carbonate or bicarbonate. And if the clarifier retention time is too long, what happens is that basically diffuses into like an acid, and it can kind of kill off the smaller organisms. So that's why larger organisms kind of proliferate under those conditions. It's more of a function of the plant, less a function of like the biological system.
Okay, great. Here's a question. It says, typically when we kickstart conventional activated sludge systems, we increase load by monitoring the MLSS. How do we kickstart MBBR systems?
Yep, very good question. Very good question. In some instances, we have added bioformula. In other instances, we add activated sludge from, say, a nearby plant, or if it's an existing plant, that helps. I would say it's more common to add activated sludge. It does help kickstart the system. I would say it does vary, but in most situations, in warm weather, good system influent, good primary treatment, you would see kind of peak biofilm growth and peak treatment for BOD systems maybe 4 to 6 weeks in, maybe less if the temperature is a little higher. Under a microscope, you'll see biofilm in a week. Visually, you'll see biofilm in a week or 2. You should see biofilm in a week or 2.
Okay, great. Let's see here. What is the important maintenance involved in MBBR, and what is the minimum instrumentation you recommend for monitoring in basins?
Yeah, very good question. Minimum maintenance. So what I typically recommend to operators is to visually check the media once a week, just to kind of keep an eye on the biofilm growth, see if it's decreasing or see if it's increasing. It would be more advantageous if you could weigh the media, say once every few months, just to kind of see, hey, am I gaining mass? Am I losing mass? Or is the average staying about the same? You know, there's a good operator tasks and kind of good indicators of the system, how well it's performing or how well it's responding to fluctuations. As far as the instrumentation, you know, for an aerobic system, it's pretty basic. A dissolved oxygen analyzer and a dissolved oxygen probe is really all you need. For a lot of small systems, that dissolved oxygen equipment may not even be required. You know, if you're looking for more energy efficient or more ways to better way to optimize energy, then you might do dissolved oxygen feedback loop. Gets a little more complicated, but can save energy over time. There's also some systems where we do on-off oxygen control based on maybe the COD reading or the ammonia reading at the end of the process. So good question.
Okay. I think that is about it. There is one more question here that I think is a good question to end on. For a true MBBR process, what is best, pre-anoxic or post-anoxic, considering no return activated sludge?
So again, it will depend on the BOD and nitrate ratio. Most applications are going to use a pre-anoxic because you have organic substance. You can't denitrify unless you have BOD in the system. So if you put an anoxic system after aerobic system, chances are you've used all of your BOD. So an anoxic system, post-anoxic system would then require external carbon addition because you can't denitrify without having BOD or organic carbon in the system. Typical rule of thumb is about 4-to-1 BOD to nitrate ratio or 8-to-1 COD to nitrate ratio for domestic systems, and that may vary with industrial systems.
Okay. Sounds good. All right, guys, we are at an hour and a half, and we really appreciate over 100 of you guys staying on board with us. We know this was quite long, but as we said, we could do an entire course on this. So I know it was a long time. We dove into a lot of different details. There's a lot more we can talk about. So if you'd like to do a one-on-one, please reach out to us. Any other questions as well, please feel free to email us at any time. And we will send out the recording of this webinar along with the slides shortly. Thank you so much for joining us.
Thanks, everyone. Okay. Kelsey, can you shut down like the attendees and keep it?
Yeah, I'm trying.